Now going to start talking about how to draw a root locus by hand. We already did the setup. We already said what root locus is. And what you have to do ahead of time is express the closed loop transfer function, actually the characteristic equation, to this form. We talked about that in previous videos. This L of S is a ratio, polynomial over a polynomial. Monic numerator and monic denominator. We talked about this earlier. Then what the root locus is going to show us is where the roots of the closed loop transfer function, where they are as this k goes from 0 to infinity. So I'm not going to talk about L of S anymore. We'll take that as a given for this video subsequent. By the way, there's going to be a bunch of rules for how to draw root locus, and they're based on the complex arithmetic of this. If this is a true statement here, that means this L must be minus 1 over k, and we're looking at non-negative k. So the magnitude of this L is 1 over k, and the angle has got to be 180 degrees because this is a real negative number. I'm not going to go through that, but if the rules that we're going to show you look strange to you, that's where they come from. So let's talk about an example. So here's our L of S. It is 1, 0 at minus 4, pole at minus 1, and complex poles at minus 3 plus or minus J4. Step 0, before you do anything, is simply plot poles and zeros of this L on the complex plane and make your scales equal. Same scale for real as you do for the imaginary axis. So here they are. Pole at minus 1, and then the complex conjugate pair at minus 3 plus or minus J4, 0 at minus 4. That's step 1. Sometimes get that wrong. Maybe because this L of S wasn't just handed to them. But if you don't get this right, everything after that is going to be wrong. Rule number 1, you can't really start drawing anything. They just tell you what's going to happen. Call the number of poles of L, call that N. In this case, there's 1, 2, 3. Call the number of zeros M. There's the 1. And N is always going to be greater than or equal to M. The number of branches of the root locus is the same as the number of poles of L. That's how many poles there's going to be of the closed loop system as well. Branches start at those poles. By branches, we mean root loci, where the roots of the closed loop characteristic equation will go as k goes from 0 to infinity. Those branches end at zeros. They're going to end here, but there's only 1, 0, and 3 poles. There are n minus m. They call them zeros at infinity. They go off to infinity in some direction. So we're going to have one branch go into this 0, and 2 other branches go off some kind of infinity someplace. Talk about that in later rules. First, where is the root locus on the real line? It's where there's an odd number of poles and zeros to the right. So just start out on the right and start moving left. No poles or zeros so far. That's 0. That's an even number. Keep moving left. Oh, we encountered a pole or 0. 1. So there's going to be on the real line left of this little pole. Keep going left. I encounter another 2, but it's a complex pair. So you can ignore them since they come in pairs. It won't change whether the count is even or odd. So still on the real line. Oop, finally, we get to here and we've got a total of 4. Even if we ignore the complex, we've got a total of 2. That's an even number. None over here, and you can keep going forever and you encounter no more poles or zeros. So the root loci on the real line are just here between this 0 and this pole. That's rule 2. Rule 3, the asymptotes. Remember those branches that go to infinity? Well, they kind of approach asymptotes. How many asymptotes and where do those asymptotes go? It depends on this n minus m. N equals m, you don't have any asymptotes. N minus m, meaning there's one more pole than there is zeros. It'll go strictly left along the real line, actually. That angle is 180 degrees. N minus m is 2, as in this case. We have 3 minus 1, that's 2. It'll be plus and minus 90, straight up and straight down. Where's the center go? We'll get to that next. And then these are the formulas for higher numbers of n minus m, where you have even more poles than zeros. Keep going kind of even angles around. The center will always be on the real line. In this case, it doesn't quite matter. There's going to be a center, but we're going to find out where it is on the real line. And here's where the center of the asymptotes are. There's a formula for it. This alpha, where it's the sum of the poles minus the sum of the zeros, and actually just the real parts, divided by that n minus m. So remember, we have, what do we have? Poles are at minus 3, and minus 1. So it's minus 3, minus 1. Minus the 0 is at minus 4, minus a minus 4. N minus m is 3 minus 1. Do this arithmetic, you get minus 3/2. So right between minus 1 and minus 2 is where the center of that asymptote is, or where it crosses the real axis. There's our asymptotes. We'll go straight up and straight down along this dotted line. I want to break this up into about 10-minute segments, so I'll postpone other rules for another video. Other videos. This is going to take pretty many videos, sorry.